Okay, this is chapter 5, section 5.4, and this is lecture 16. And in this lecture, we'll be talking about centroids of 3D objects. So hopefully the last lecture made sense and that you understand what's going on with 2D centroids. Again, just using simple geometry and following the equation that I showed you, it really wouldn't matter if I gave you 2 objects or 50, as long as you can find this individual center of each of those objects, then you can just add them together and find the overall composite centroid. So the same thing is true in 3 dimensions, just now we have X, Y, and Z. So if you look in your book again, there is a table of varying shapes. And for example, the hemisphere, we're going to be using that in this first example. And so to find the X bar of the hemisphere, it's 3a over 8. And as we know, 4/3 pi r cubed is the volume of the sphere. So it makes sense that half is going to be 2/3 pi r cubed, or a in this case. And so then there's the ellipsoid. So you would have to be told, what it was. But obviously if a over h is different, then it's obviously not a sphere or a hemisphere. And then there's something slightly different, and then the cone and a pyramid. So those are the 5 major ones. The cone and the hemisphere are the ones we use the most, I would say. All right, so your worksheet 16 has this, and this is just a 3D object. So a planal 3D object. It's the only difference is I've made this a little different, is I've added density. So in this example, you have the block on the bottom has a density of 0.1 pound per inch cubed. And the triangle that's a slightly different color has a density of 0.25 pound per inch cubed. Now, the way you deal with this is that, let's just stop here. So that density is equal to mass per unit volume. And so usually we're saying we're finding the center of mass, right? But if we want to substitute that, then we know that's just going to be equal to rho times volume. And so the only difference in what we do is when we go ahead and we do center of gravity, center of mass, is normally, you recall, our first column would be area, or it could be volume. And now in this case, it could be mass, and it could finally be weight. So the idea then is all of these are essentially going to give you the same result. And so we're treating, in this example, because we're dealing pounds, we're not differentiating between pound mass and pound force. So we're going to treat it as a center of weight, and it could have been pound force, pound mass. So anyway, I'm not trying to confuse you. Just the main thing is that for this column, what you're going to do is, normally what you would do with a 3D where everything was the same, you'd have volume, and then you have your, let's just say, meters cubed. And then next to it, you'd have your X bar, and then you have your Y bar, then you have your C bar, and then you have your X bar times volume, Y bar volume, and C bar volume. And so you'd put in your numbers and you'd get the sum of your volume. Here, you then find the respective centroids for each piece. And then again, you get the sum of the X bar volumes and sum of Y bar volumes, sum of C bar volume. And so then your final equation would be big X bar would just be the sum of the X bar volumes over the sum of volumes. So the only thing different in what we're doing is, because we can't just use volume because we're doing center of mass or center of weight, and because the density is different, that's going to alter it. But so we're simply going to substitute in here, we're going to put in this W, which we know we can get by just multiplying by rho times V. All right, so we can say in this case that our column here would be replaced with weight, and then we'd have the respective columns, and with weight just being equal to rho times the volume. All right, so we'd find rho times volume and do it. All right, so going back to our object, and so I'm going to go ahead and show it to you up close, and I'm doing this again because the focus is an issue. But here we have our shape, and I've drawn the dimensions 2.5, 2.5, 2.25, 2.25, and of course it's good if you have the printed one in front of you so you can see this at 3 high, and then and then this is 3 high here. And so the what I've done over here is this is triangle. So what I'm writing here is the x bar of the triangle. So the x bar of the triangle, well, we know in the x-axis going this way, it's going to be 1/3 of the height. Well, in the x direction, the height is going to be 4.5, right? 2.25 plus 2.25. And so what we end up with is 1/3, 4.5. And then, which is just 1.5, right? And then we have y in the y direction, the height is going to be 0.5 because it's 3 inches tall. I'm sorry, y going this way, it's 1 inch going this way. And so since we're cutting the triangle in half, the center is just going to be in half of it. It has nothing to do with h/3 because we're just cutting the thing in 2 sections. So we know the centroid is right there, 0.5 in the y direction. And then the z direction, we know that because it's 3 high, we know that 1/3 of 3 is 1, so that would be that. But then we also have to add on this extra height. And since the block is 3 inches, we basically have 3 inches plus this extra 1 inch. And that's what gives us this. All right. Okay. So let's go down here and this will give you a chance to fill out your table. So we're calling the block 1, we're calling the triangle 2, and we're calling this little empty vacant hemisphere 3. So if we go down here for block 2, we calculated our x, y, and z, didn't we? 1.5, 0.5, and 4. So go ahead and fill that in for 2 in the row that you're given. So let's go back now and let's look at the centers for the block, and then we'll get to the weights. But let's just look at the center. So centers for the block are going to be x bar is going to be 2.25. That makes sense because you're going basically halfway out this direction. And then for the height, it's going to be 1.5, essentially half of 3, right? And then for y bar, you have the total distance is 6. And so what I didn't draw here, which might help, is that's 1 inch too. And if you look at your diagram, you can see that. So it's basically 6 inches. So half of that's going to be 3. And that's where we get to 2.25, 3, and 1.5. All right. Okay. And then lastly, we have the hemisphere. So let's look at its centroids. And then we'll come back to the weight for these. So the hemisphere, for a hemisphere, we know that the volume of a hemisphere is 2/3 pi r cubed. So if I multiply 2/3 pi times 1 cubed, I get 2.094 inches cubed. All right. So when I'm looking at the actual center point for that, then that's the area. And let's come back, I'm sorry, that's the volume. Let's come back to the location. We know that it's 3/8 r, or essentially 3/8 the radius. So since the radius is 1, we know it's basically 3/8, it is 3/8 of an inch. Again, that's from the base up. That's going from something like this up to here, right? Not from the top down. And since this is upside down, we essentially are going to take 3 inches to where the base is, and we're going to subtract off 3/8 of an inch, because we have to go, think about our object, it's like this. There's our hemisphere. That's 3 inches. This here is the 3/8 height. And so we want this height here. So 3 minus 3/8. And so that's going to give us, for that, 2.625. Okay. So 2.625. And that's what we get when we subtract 3. Then let's look at the y bar. So for y bar, it just bisects it. So it's 1 plus 2.5. That goes right through the center. So y bar is 3.5 for the hemisphere. And then lastly, the x bar. So x bar, again, it's right in the center. And so 2.25. You see my chicken scratches? And that goes right through the center there, 2.25. All right. So now we're done. We have our locations of all x, y, and z. So now we're going to go ahead and we just need to figure out the weights. So weight 1 is just going to be the density times the volume, just like I talked about. So weight 1 for the cube is 0.1. So 0.1 pounds per inch cubed is going to give us a total of 8.1 pounds. We multiply that. Weight 2, we're going to multiply by 1/2 base times height, and that will give us our, sorry about that pause. I had to, for some reason I had the wrong, density here, but the numbers were from the right density. So 0.25 pounds per inch cubed, 1/2 base times height times thickness. So 4.5 for the base times height, 1 inch thick, times that. That gives us a weight of 1.6875 pounds for the triangle. And now we just need to subtract off this. That was where this came down here. So 0.2904 inches cubed. We assume since it was in the block, it has the same density as the block, or lack thereof. So if we multiply that by 0.1, we just get 0.2094, and that would be in pounds, and that's going to be negative, so we subtract that off. So now we have all three, and accounted for the weight. Go through, sum that to 9.5781. I just carried extra sig figs. And then we go ahead, do our multiply through x bar times weight, y bar times weight, z bar times weight. These are our numbers. Go ahead, add them all up like before, and then simply divide. So you have 20.285 divided by 9.578. You get 2.12. And 24 divided by the total weight, 18.3 divided by total weight. That gives you your subsequent values. You look at them, do they make sense? Yes, they do, based on the geometry of this. And so that's good. So it really wouldn't matter what other shape I gave you. If there's, I could have given you something else at the end, maybe a sphere on top. And so again, as long as you just systematically keep track of each piece as a 1, 2, 3, 4 as in terms of shapes, then you're fine. Okay, so that's a three-dimensional problem, and they really don't vary much from that. So I want to do one more three-dimensional, and this one is something where you have essentially no thickness. And there's a homework problem like this where you calculate the centroid of a potato chip, or it looks like a potato chip. And here we have our sheet metal garbage can. So in this case, we have a hemisphere or quarter sphere, and then we have two flat sides, and then we have a solid bottom. And so the top is, so we have to treat this as 4 different pieces. We have 2 sides, we have the outer arc, and then we have the quarter circle at the bottom. And so let's go ahead and go through this. All right. Again, let me show you, walk you through this slowly. So here we have it's 16 inches, 10 by 10, solid bottom. Now from symmetry, we can say that X equals Z bar. So we just pick one, solve for the other. So one thing to note too is that when you look at this thing, for example, this piece of sheet metal here on this side, and what I've done is I've labeled them 1, 2, and 3, because this lies right on the Z axis, and we assume the thickness is 0, that means that the centroid of this piece in the X direction is also going to be 0. And so the same can be said for this piece here too, since it lies in the XY plane, the Z bar for that is going to be 0. Now when we treat this outer section, again, that's not a solid, it's a line, so we have to use the line centroid, or 2r over pi, to find that. So here we have 1 and 2 are rectangles, 3 is a quarter circle surface, and 4 is a quarter circle on the bottom. So area of 1 and 2, base times height, so 10 times 16 gives me 160 inches squared for each one. And then, so if I come down here, I have my area, 160, 160. And then for my quarter circle arc, I know that the area is just going to be, normally be 2 pi, but 2 pi r times the radius. But in this case, because it's a quarter, it's going to be pi over 4 times the radius. And so we know in this case that the radius is 10, right? So because it's 10, we end up with the quarter circle arc. We end up with, where is it? Right here, area for, well, that's actually the center. Okay, so this is a little confusing written out here. So what I did is, let's look at the 2 shapes. So we have the quarter arc, which encompasses the entire outside of the can. So we want to know where its X bar is. So we know that's 2 over pi, which is 2 times 10, which is 20 over pi, which gives us 6.366 inches. And then the area. So the area is going to be the quarter arc, or pi over 2. So 2 pi r, then divided by 4, and then times its height. So we have pi times 10 times 16 over 2, or 80 pi. And 80 pi is essentially 251.33. Then if we look at the base of the can, which is a solid quarter, then we know the area is pi over 4 r squared, which is pi over 4 times 10 squared, which gives us 78.54 inches squared. X bar being 4r over 3 pi gives us 40 over 3 pi, where r is 10. X is 4.244 inches squared. Inches squared. There we go. All right, that makes lots of sense. So we come back here and we plug those in. So we have our area, 251.33, 78.54 for the respective parts. X bar, 6.366 and 4.244. So let's look at the X bar. So we know for one, like I said, since it's here, it's 0. And for here, it's going to be half. So it's 0 and then 5. And then for the numbers we got before, we got 6.366. So that's the 6.366 here, and the 4.244, 4.244. So that's my X bar. I don't need Z bar since it's symmetrical. So then it's just the Y bar. And so Y bar is easy. From the height stand, it's just halfway up. And since it's 16, we know halfway up on 1, 2, and 3 is all 8. And then 4, since it's right at the origin, it's going to be 0. So you come back to that, 8, 8. So go ahead and multiply through like before, and that's the easy part. So once you get this, the rest of this just rote math. You get 2733.3, 4570.6. You could have rounded it if you'd like, and then go ahead and subsequently divide, and we get X bar 4.21, Y bar 7.03. And that's pretty much it. That's all there is to this. And so what I've shown you are the two examples of 3D, one with varying density and one with thin sheets. And that's essentially it. Those are the two. So again, quick recap of this. We had this, these 4 surfaces. We knew X and Z symmetrical. We had the 4. I showed you on this sheet how I found the respective X bars and the areas for the quarter circles. For the 2 sides, that was easy because they're just rectangles. And then we just plugged everything in and we solved. We got our values. Okay. Well, I hope that helped. So that's it for centroids. That's all we're going to talk about. 2D, 3D composite. Now we're going to take this, and the next step is to talk about a moment of inertia, and that will be in lecture 17. Thank you.